Becoming good at Lewis structures really takes some practice. So in this video, we are going to practice drawing some Lewis structures, and then we're going to learn about VSEPR theory and apply it to a concept called polarity. So to begin with, this is our list of all of the compounds that we are going to draw. We could draw a Lewis structure for each one of these compounds, but we're just going to pick one from each shape. Now this molecular shape is basically a description of what shape would the molecule be if we're looking at the molecules or at the atoms themselves, and based on how they would be bent because of electrons. And that's where that VSEPR theory comes from. Valence shell electron pair repulsion. So we're going to just pick one molecule from each group and draw it, and then we're going to apply VSEPR theory to it to figure out why it is the shape that it is. So these are the 6 that we are going to draw. So let's just start one by one, and we're going to do the whole need, have, and then determine the number of bonds to help us draw the structure. So need, have, bonds. So first off, how many do we have? So this is the same thing we did in the last video. So for HCN, hydrogen cyanide or cyanic acid. So first off, hydrogen, it has 1 valence electron. Carbon has 4 valence electrons. Nitrogen has 5. So 1 plus 4 plus 5 gives us our 10. Hydrogen wants to have 2, carbon wants to have 8, and nitrogen wants to have 8. That's 18. 18 minus 10 is 8. Divided by 2 is 4. So there should be 4 bonds. So I'm going to draw it with H to a C to an N. Carbon is the least electronegative, so it goes in the middle. I've drawn my 4 bonds. That means I have a total of 2 electrons remaining, because remember I have 10 electrons, and this is my structure. Now I didn't draw my 2 electrons here because hydrogen can only have 1 bond. That also is why hydrogen to carbon has 1 bond, and then this triple bond is all your 3 bonds remaining. And that's the appropriate structure for hydrogen cyanide. For the next one, with the CH2O. Carbon has 4 valence electrons. Hydrogen each has 1, but there are 2 atoms. And then oxygen has 6. So 4 plus 2 plus 6 is 12. Carbon wants to have 8. Hydrogen wants to have 2, but there's 2 atoms, so 2 plus 2 is 4. Oxygen wants to have 8, and that's 20. And then divide by 2 equals 4 bonds. So then out of this compound, the first thing we think about is what atom is the least electronegative. That's carbon, so carbon goes in the middle. I then need to attach it to with hydrogen. There's 2 hydrogens attached to it, and then there's also an oxygen. So hopefully you realize hydrogen can only have a single bond. That leaves me with 2 bonds remaining to attach to my oxygen. And then I fill in my remaining electrons. I'm going pretty fast because I know we've covered this theory before, so what I recommend doing is stopping the video for each one, working out how many bonds it has, attempting to draw the Lewis structure, and then check your work. Because then it's a lot easier to say, ah, yes, blah, 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 4 plus 2 plus 6 gives me 12, that kind of thing. So do stop the video, try this, and then check your work, and do it one by one. I'm going to keep the video rolling with step by step drawing each compound. All right, silicon tetrachloride. So we've got 1 silicon and 4 chlorines, which means silicon has 4 in its outer shell, chlorine has 7 in its outer shell, but there are 4 chlorine atoms, so 7 times 4 gives me 28, and then there's a total of 32, 4 plus 28. Then over here, silicon wants to have 8, chlorine wants to have 8, so there's 5 total atoms that want to have 8, so I just did 8 times 5 to give me 40. 40 minus 32 is 8, divided by 2 is 4, so 4 bonds. 1 central atom is your silicon, being the least electronegative. Each chlorine is around it, and now we spread our 32 electrons around it. And then yes, if you check all of these, you'll see that they all are happy with a satisfied valence. Now my phosphorus trichloride. So phosphorus has 5 electrons in its valence shell. Chlorine has 7. There are 3 chlorine atoms, which gives me 21. 5 plus 21 yields 26. Then as far as need goes, phosphorus and chlorine both want to have 8 in its valence shell. 8 times 4 gives me 32. 32 minus 26 is going to be 6. Divided by 2 is 3 bonds, which means single bonds all around. Now, what's kind of cool is when you put 8 here, 8 here, 8 here, that leaves you with 2 electrons left over, which means you have 2 remaining electrons. You can't force chlorine to have 10. It's not going to be happy. But phosphorus, it's unhappy right now because without those 2 electrons, it would only have 6 electrons around it. Now it's got 8 electrons around it. 2 from this bond, 2 from this bond, 2 from this bond, and 2 from this lone pair. So now that's a happy structure. Let's do the next one, H2S. So, hydrogen has 1 electron in its valence shell. There's 2 atoms, so that's 2 plus 6. Sulfur has 6 in it to give me 8 is how many I have. Then hydrogen wants to have 2, the other hydrogen wants to have 2, and the sulfur wants to have 8 to give me a total of 12. 12 minus 8 is 4. 4 divided by 2 gives me 2 bonds, which means I have sulfur in the middle because hydrogen can't be. 2 bonds total, and then put your remaining 4 electrons, so there was 8 total around this whole atom. So now that's my structure. Alright, O3 is my last molecule we're going to do for this video. So with this one, you have 6 valence electrons, so 6 times 3 gives me 18. Each oxygen wants to have 8. 8 times 3 is 24. 24 minus 18 gives me 6. 6 divided by 2 is 3. So I should have 3 bonds total. Alright, so you could have drawn these two bonds here, or you could have drawn them over here. It doesn't matter. Okay, they're the same thing. But what's important is every oxygen has 8 electrons around it, which means it's stable. This is the thing called resonance I was talking about a little bit last week. But like I said before, don't worry about resonance. Alright, so now we have drawn all of our Lewis structures. So now the biggest question is, what does the shape look like? So meaning, is this hydrogen to this carbon to this nitrogen, is it all in a line? Or is it like a triangle? What is it? Well, what these numbers mean. So you'll look over here where it says number of bonded atoms. This should tell you how many things are around the central atom. So meaning, if my central atom in this molecule is carbon, I have 1 hydrogen and 1 nitrogen bound to the central atom, which means it fits into this table as 2 bonded atoms, no lone pairs, therefore it is linear. This next one, carbon is in the middle, which means there's 3 atoms around it. So it is 3 bonded atoms, which gives it the description of trigonal planar. What that means is if you connect these 3 outer atoms, it looks like a triangle, and they are all in the same plane. It's not really a 3D. I mean, everything is 3D, but it's in the same plane. Then for this next one, there are 4 atoms, 4 chlorine atoms around the central carbon, which means it's tetrahedral. And there are some really pretty pictures in your book of what the tetrahedral shape looks like. Okay, so then for this next one, what about this one? Not only is there 3 atoms around the outer shell, but we have to get a little more specific, because now my question is 3 could go be here where there's no lone pairs, or 3 could be the number of atoms plus 1 lone pair, which we have. And so you'll notice here there's lone pairs on each of these N3 molecules. So in this case, you have 3 atoms and 1 lone pair. 3 atoms and 1 lone pair, which means it's trigonal pyramidal, which literally looks like a pyramid with a triangle base. And then here, it looks like the molecule is bent, like it was linear, and then we just kind of bent it in half. Same thing for this O3. It looks bent. But how you name it is if it's got 2 atoms attached to it and 2 lone pairs, it's considered a molecular shape of bent. And then same thing here. 2 atoms attached to the central atom with 1 lone pair, it's also considered bent. So VSEPR theory is just a fancy way of saying highlight the things that are around the central atom and then use this chart to tell you what the name of it is. Alright, so let's practice. I want you to pause the video. I want you to write down A through G, and I want you to try to determine the molecular shape of each of the following Lewis structures. Alright, so for A, you have 4 atoms surrounding a central atom. So it is tetrahedral. For B, you have 3 atoms around a central atom and no lone pairs. So you are trigonal planar. For C, you have a central atom with 2 atoms attached to it, so it's linear. For D, you have a lone pair attached to the central atom plus 2 atoms. So that's 2 bonded atoms and 1 lone pair, so it's bent. For E, you have 3 atoms around it and 1 lone pair, so it's trigonal pyramidal. For F, you have 2 atoms around it and 2 lone pairs, so it's bent. And then for water, which you'll see a ton, you have 2 atoms around the oxygen plus 2 lone pairs, so it's bent. Alright, so how does this help you figure out things are polar or nonpolar? Polar or nonpolar is just basically asking the question, is this a symmetric molecule? And so when you're thinking about symmetry, you have to figure out, okay, well, what does that molecular geometry, what does that mean? So for instance, with C is really easy to see. You can see it's symmetric and it's linear. So everything's pulling away from each other equally and oppositely. Now what is this thing called pulling? Well, look right here at this arrow symbol. That is called a dipole. With a dipole, you have a positive end, so literally this end of the arrow looks like a plus sign. It's pointing toward the more negative atom. So for carbon bound to chlorine, there's something called a dipole. There's a bond dipole that goes from carbon with this plus side of the arrow pointing toward chlorine. Because if you look at carbon's about 2.5, whereas chlorine is 3.0, which means of this covalent bond where these electrons are shared between the 2 atoms, the majority of the electrons are on the chlorine side. So even though these electrons are moving around like crazy and sometimes they're next to carbon, they spend most of their time next to chlorine because they like it more. It's more electronegative. So this means that each of these chlorines is pulling outward, but it's tetrahedral. So they're all pulling equally out from the central molecule. So it is nonpolar. It's symmetric. All right, what about molecule B? So this is trigonal planar, so they're all pulling in opposite directions like a triangle. But the thing you have to remember is that they're different atoms now, so it's not a symmetric molecule, which means the electrons are going to be wanting oxygen more than either of the chlorines. So this oxygen is sort of like tug of war. It's the strong man. It's going to be pulling most of the electrons toward itself, which means it's going to be a polar molecule. So here it is, it's not symmetric, oxygen's pulling more of the electrons toward it, it's winning the tug of war. So when you're asking polar or nonpolar, you're just asking, what would win in a tug of war contest? Will you be sitting there stagnant for a long period of time, or will the rope actually move? And then this last one, it's very symmetric. The sulfurs will both be pulling outward because sulfur is not going to be pulling outward. It's going to be a very nonpolar bond because carbon and sulfur have the same electronegativity value, so they're pulling equally. So this is a very, very nonpolar molecule. Let's try some more. So with D, you have a bent molecule. So in this case, fluorine is pulling the most. That's definitely going to be a polar. You've got some lone pairs on the nitrogen, you have oxygen over there. All these things are very electronegative. Everything's fighting for electron density. Fluorine wants it the most. So with this, you're going to have a polar compound. It's not symmetric. Think about it. If you could place a mirror in the middle, to put a mirror on the nitrogen, would both sides of the mirror be the exact same? And if it's not symmetric, and therefore the answer is polar. What about this last one? You've got chlorine attached to phosphorus, and there's 3 of the chlorines, but you also have that lone pair. So if you go back and you look at your chart, you'll notice 3 bonded atoms, 1 lone pair, therefore it's trigonal pyramidal. So what's crazy about this, you've got your lone pair that's kind of up on top of a pyramid. And so that being said, the chlorines are all pulling away from the phosphorus, your 1 lone pair is pulling up, but it's not a symmetric pulling. So therefore it's going to be a polar bond. Alright, what about these? Are these nonpolar or polar? So with our F molecule, your chlorines are both pulling equally out and oppositely if it were linear. But this is where it's helpful to not just trust the way something is drawn. You have to think about what it looks like in 3D space. So remember, this would be a bent molecule. So a better way of drawing it would be like water shown here for G, where you can see that the hydrogens are not pulling equally and oppositely of those 2 electron pairs. if you were to place a mirror right here across the oxygen, you would see that the lone pairs are on one side of the mirror and the hydrogens on the other, so it's not symmetric. The hydrogens are pushing, these electrons are pulling it up, so the whole magnetic moment is up. So if you were to place it toward a magnet, this negative side of the molecule would go toward a positive pole. Same thing here. So this molecule is going to essentially look the same thing as this, except for your chlorines are pulling down, your electrons up here are pulling up, and so they're both going to be polar. And with that, give it a try. Go complete all of your homework for Chapter 4.